So we've reached chapter 8, and this chapter really begins our first entry into true inferential statistics. Because what we're going to be doing from here on out is we have a population with some mean, and we don't know what that mean is. And it's something that's very difficult, very costly, or impossible to find out what the mean is. So we're going to be using samples and sample means in order to find that out. So the first thing we're going to talk about is a point estimate. Now, a point estimate, don't get too bogged down in the definitions here, but a point estimate, that's the value of the statistic that we use to estimate the parameter. So in other words, the point estimate for mu is just X bar. So if I'm asking for a point estimate, you can just give me X bar if I ask for a point estimate from you. Now remember, X bar, our point estimate, has its very own distribution. We learned that in chapter 7. We also learned that it's not likely to be exactly correct, especially if it's normally distributed. Then probability that it's exactly correct is pretty much 0. Now, for more discrete data, yeah, it can be, but generally speaking, it is not. So it's very unlikely. And you will notice when we do the activity in class for the dice rolling, very few people get exactly an average of 7. Some people do, but it's very unlikely. So generally speaking, it's better to create an interval for which we can be reasonably certain the true population mean falls. And that's kind of what we're going to be doing with the confidence interval right here. Now, the best point estimate for sigma is S, but we will not be looking at those directly. If you want, you can reference chapter 11, and it kind of tells you how to make inferences about the population standard deviation. It's not something we do often, so that's why it's not really a big, important thing to include in the class. So later we will, in chapter 12, we will investigate the point estimate for a population proportion. So we'll be doing that later on, kind of a yes or no question, binomially distributed variable, basically, is kind of what we're doing there. Okay, so let's talk about what a confidence interval is. Confidence interval is an interval of numbers that we're relatively certain. We'll talk about what that means, relatively certain. That sounds really vague, but we'll actually give it numbers, that the true parameter falls. So we use the point estimate to find these, and we use other information to determine this lower and an upper bounds. So I will show you how to figure that out both by hand and using your TI calculators. So confidence level, that's going to be how certain we are that the parameter lies. That's our relatively certain. We're actually going to have a number associated with that. And that's going to be our confidence level. So one thing I really want you guys to be careful about is the difference between confidence and probability. So we won't be talking about probability necessarily, because the probability that mu falls in an interval is really only 1 or 0. Why? Because mu is not a random variable. It is simply a constant that we don't know. So think about it. What is the probability that 2 lies between 1 and 3? 1, right? What is the probability that 2 lies between 3 and 5? 0. So that's essentially the same thing as saying the probability that mu falls between two numbers. It's either 0 or 1. So that's why we use the word confidence instead of probability. So you'll see that illustrated a little more in just a moment. So we're going to be using a general formula to figure out our confidence interval. And this uses information from our sample and the central limit theorem. So remember by the central limit theorem that x bar is normal, or approximately normal at least, with mean mu and standard deviation sigma over the square root of n for large n. And remember, what large actually is depends on the distribution of x. So we talked about that in chapter 7. Of course, if we don't know anything about the distribution of x, then n needs to be at least 30. If we know that x is normally distributed, it does not matter. It doesn't necessarily have to be large. It can be any number n. And if we just know that x is symmetric, not necessarily perfectly normally distributed, then 15 will be sufficient. So I want you to think about the area under the normal curve, and this is the distribution of x bar. So it's got the normal curve, assuming that it meets the assumptions for the central limit theorem to hold. So we have our normal curve, and we go, okay, here's our mu, because the mean of x bar is mu. And then we know that 95% of our data will fall within 1.96 standard deviations, this being sigma of x bar. So remember, sigma of x bar is sigma over the square root of n. So we're 1.96 standard deviations to the left and to the right of mu. So what you do is you go out and you get your sample. Okay, let's say it's here. So that falls within my 95%. So this can have a probability associated with it. We have the probability that x bar is between these two numbers is 95%, and this one does. But 5% of them are going to fall outside here. And that's going to be where we do not contain the true mean. So you'll see that in just a minute. So let's take an example so that I can illustrate this better. That's a blank page. Unfortunately, it got kind of caught in here. So let's say we have a university administrator. They're interested in determining the average IQ of all their professors. So it's a large university, so it's too costly. We're not going to test all the professors. So they select a random sample of 20 professors. Each one is given an IQ test, and the results show a sample mean of 135. And since the test is nationally standardized, we know that sigma for population is 15. So how would the administrator estimate the average IQ for all university professors? So their point estimate is 135. So that is your point estimate from you, and that is very unlikely to be exactly right. So we're going to take all the information that we have, and we're going to create a distribution out of this. So in order to do that, in order to say, well, how good is this, we need to know the shape of the distribution. Well, IQ scores, we've done this before, are normally distributed. So even with an n equals 20, x bar will also be normal. The mean will be mu, the true mean, and standard deviation of the sampling distribution. So what is the standard deviation? Sigma over the square root of n. So that's going to be 15 over the square root of 20. Let's grab that real quick. What is that? So I want to point out that we do not know this answer. Our mu is unknown because this is what we're trying to figure out. So 15 divided by square root of 20 is equal to 3.354. So we have all the information we need. So what we can do is we can display this graphically. So I guess they went 3.35, that's fine. So we know that within one standard deviation of the mean, we know about 68% of our data fall here, okay, within this part right here. So let's look at the next one. So using that standard deviation, we can find a bound on the estimate. We know 95% of the observations will fall within 1.96 standard deviations of the mean. That was the picture we had before. So if we take 1.96 times 3.35, we get 6.57. We know the maximum distance that our estimate will miss the population parameter 95% of the time. So what is that? What am I saying? Let's look at this picture. So we're saying that here's our mean that we don't know right here. And here we have the mean plus 1.96 standard deviations. So 1.96 times 3.35 and 1.96 times 3.35 below mu. So we know that 95% of the time X bar, so if we go out and get different samples, 95% of my samples will be between this number and this number. So again, we're not going to go out and get a bunch of samples. We just want to use this distribution to know how good our sample is going to be. So what we're going to do is we're going to throw a net. Okay? We're going to throw a net centered at whatever X bar we get. So again, what happens if it's right here? That's within the 95%. So what happens is, here's this X bar that we tossed. So we tossed an X bar and we landed. And if you take this and you take this piece and this X bar and you add 6.57 and subtract 6.57, so essentially what you're doing is you're moving these to here. Well, since this is less than 6.57 units away from the true mean, then the interval, which is 6.57 away on either side of X bar, should contain the true mean. And 95% of these will, because there's a 95% chance the sample mean will be between this and this. And therefore, the interval that we create will catch the sample mean 95% of the time. So I want you to think of a confidence interval as a net. Is this net going to catch this fish? So we're going to center our net right here where we got a point estimate where we think it is, and we got our net and we caught it this time. And we will catch it 95% of the time. So, important idea here. When we construct it, we're not saying that the parameter is in the middle, but somewhere in that interval. We know it may be not. So like I said, it's like throwing a net into the sea. We hope to catch a fish. We don't know where the fish is. And we're really hungry, so we throw a big net. So statistically, that's a higher degree of confidence. So if I up my confidence, I throw a bigger net. If I lower my confidence, I throw a smaller net. We'll talk about that in just a second. So how often will the 95% confidence interval capture mu? Well, 95% of the time. And that's what we mean by that. So we're tossing this net and we caught it. Oh, that's the same thing. Oh, well. And then, so here's another net that I've thrown. So 5 in 100 samples. So I've tossed this net and I've ended up outside of the 95% area. So if this is outside, so if this distance is 6.57 and this distance is 6.57, oops, it just misses it. So this is going to happen about 5 in 100 times, that I'm going to have my X bar and my confidence interval isn't going to catch the true mean. And you just have to kind of be okay with that. Most of the time it is. 95% of the time it catches the true mean. Every once in a while, by random chance, you're outside of it. Okay, so here's another picture of that. So here is a bunch of confidence intervals that somebody made. So we made a bunch of confidence intervals. Okay, sorry, OneNote doesn't like me. So these are, let's say these are a bunch of confidence intervals that we've done. And you'll notice that one of them does not catch the true mean. The rest of them do. So about 19 out of 20, which is 95%. So that's what we expect to happen. Of course, it's a sample of samples. It may be not exactly 95%. The other issue with it being exactly 95% is also that most of the time, remember, we're only approximately normal and not exactly normally distributed. So that also moves that confidence interval a bit. So let's talk about finding our confidence intervals by hand a little bit, and then we will go and learn how to do them on the calculator as well. So you want to, number one, you want to make sure your assumptions are met. Okay, the data is from a simple random sample. Okay, other types of sampling techniques require us to multiply by another number in order to get it to be accurate, because the randomization is different. The population is normally distributed, or the sample size is large, at least 30, of course 15 for symmetric data. The sigma, the population standard deviation, is known, or the sample size is extremely large, and extremely large being like over 1,000. Mostly we're going to restrict ourselves to when sigma is known. And then number two, we're going to find the appropriate z by taking 1 minus the confidence level divided by 2, and then finding the appropriate z-score using INV norm. So the way that I could find all of these z-scores, if I have a confidence level of 90%, then I want 0.1 over 2, which is 0.05, and I want to use INV norm. Now remember, if I give it 0.05, INV norm is going to assume that's an area to the left and give me a negative number. So I actually have to use 0.95, and that'll give me 1.645. And then 95%, I have to use INV norm. Oops. This is 0.05 over 2, which is 0.025. So I have to use INV norm of the opposite of that is 0.975. For this one, for 98%, I need to use 0.2 or 0.02 over 2, which is 0.01. So INV norm of 0.99. And for this one, 0.01 over 2, which is 0.005, I had to use INV norm of 0.995. So a nice way to do this is just have these and remember what these are: your confidence level and your z-score. So it's nice to have, say, this table written on your cheat sheet for the test, so that not only, even if you're using the calculator to find confidence intervals, there are some sample size things we're going to be doing later on that the calculator doesn't do. So this is an important chart to have in your test notes. Okay, So finding the appropriate z-score depending on what my confidence level is. And then I use this formula. X bar minus my z-score times sigma over the square root of n, which is basically what we did. Z-score being how many standard deviations we want to be away, this being the standard deviation of x bar. And then the mu is between this, the minus, and the plus. Okay, so that's how you find your confidence interval. We interpret the confidence interval like this. We are 95, whatever, percent confident that the true mean lies between this number and this number. And that's what we put right there. We could also say something like 95% of confidence intervals constructed will contain the true mean. But the problem with this is this doesn't really tell me, and then a lot of times I put units on this one. This doesn't really conclude anything about the actual subject that we're talking about. It's more of an interpretation of a confidence interval. So, like I said, the confidence intervals is exact for normal populations and approximate for large samples of non-normal populations. So something we have to be very careful about. Okay, so let's talk about finding one in our TI calculator. So let's find the confidence interval for the example that we had. So remember we know that X bar was 135. We were given that sigma is 15, and we had a sample size of 20. And we want to find this confidence interval. So what we're going to do is we're going to go to our calculator and move this a little bit, make this smaller so I can see what I'm doing. Okay. So we go to our calculator, turned on. Being on is nice. So we make sure our assumptions are met, of course. We go to stat. You go over here to tests. It's not actually going to be a test. Now, those of you who have different calculators, if you have an 89, this is the TI 8384 series that I'm talking about here. If you have an 89 or Nspire, you actually, or of a Casio, you actually do have intervals. So what you're going to want to do is you can find under the same place, under a similar place where you go to statistics, you can find intervals. This is something, if you need to look it up, look up on YouTube. And this is a Z interval on your calculator. I'm not sure. I'll try to put them on the in the module for chapter 8 so that you can actually go look at that and get an exact way to do it. So we're not going to do a test because that is later on. That's chapter 9. We're going to number 7, Z interval. So you can either scroll down to it or you can just also hit 7. So it brings up a menu. So for our purposes, we're going to use statistics. Data is when you have data. So I wasn't given the statistics. I was simply given a list of data and a sigma and told to go do this. So right now I have statistics. So we want to go to the side, highlight stats, and hit enter. Because whenever you highlight something, it doesn't stay until you hit enter. So then hit the down arrow. That's this down arrow. And then sigma. Enter the population standard deviation. Do not divide anything. The calculator is doing that for you. So the standard deviation that was given in the problem is 15. Then enter X bar. Enter the sample mean that we're given. We're given 135. Sometimes we're given the sum of the data. In that case, we would enter it and divide by, so you might be given sum of the data. You can enter the sum divided by n, and it'll automatically calculate this for you. So we were given the actual X bar, so we're putting in X bar. And then n, we're going to enter 20. And then our confidence level, we're doing 95, so 0.95. And we hit our number. So we have it says 128 to 141. So here's our interval. So we can write it like this. This is my preferred method because it kind of gives me an idea of what actually is going on. Okay, so we want to state our conclusion, and our conclusion is we are 95% confident the true mean IQ score of professors is between 128.43 and 141.57. That's all you have to say. I don't have units on this, so if this was not IQ test and it was something else, then I would put the units inches or feet or whatever. Okay. So, like I said, you're given the answer. You're going to report it in interval notation like this, or you can use this. And so we did that already. We said that right up here, and we interpreted it, and we're done, and that's all. So let's do another example right here. So in this case, I was given data, but I was also given sigma, and I've been told what the X bar actually is. So I can go in here again, stat, tests, number 7, give statistics. It says the sigma is 44.7, 194.083, N is 12, and I want a 95% confidence interval. And look what we got. 168.79 to 219.37. Oh, that might be a typo. It is a typo, actually, because I'm looking at this going, yep, that is supposed to be 3. Okay, so if you look at this, this is what your calculator did. It took your X bar, it adds and subtracts your 1.96, this is your Z, your 44.7, which is your sigma, and the square root of your N, which is 12. So you figure this part out first. And then you add and subtract it to your 194.083, and you have your answer. So looking at this, if I were going to do this by hand, I'm just going to go 1.96 times 44.7 divided by the square root of 12. So I'm going to do this piece first. Get my answer, 25.291. Then I'm going to type in my X bar. I'm going to add this number. And your calculator should be able to do this. I just hit the up arrow to grab it. And I get that. Then I'm going to do it. It was 374. It was a typo right there. This will take me a second. It's much faster with a real calculator because you can push these buttons a little faster. And then I'm going to hit minus and do the minus side, and I get 168.79. I guess that should have been 792, but I had some round off up here, so. Okay. So the interpretation, we are 95% confident that the true mean lies between 168.791 and 219.974. So exactly what the calculator gave me as well. So let's do one more. So we have ages and years of 50 randomly selected people in the civilian labor force. Now I'm not going to actually do this example, but we did 2 confidence intervals for this. We did a 90% and a 95%. So if I only need to be 90% confident, notice that my net can be smaller. So the lower the confidence level, means a shorter confidence interval. And when I go up to 95, it goes out farther. Now, if I go up to 99, it would be even bigger. Because if I'm going to be more confident that I'm going to catch that fish, my net's going to have to keep getting bigger in order to catch it. And I think, yep, margin of error. So that is it for today. It's only 30 minutes. So we'll be doing a kind of a fun thing in class. We're going to be rolling die. So make sure that you come to class this time because you're going to need to because of the dice rolls. Thank you.